Welcome to Math with Michelle, where math finally makes sense. Whether you're tackling high school math or diving into college algebra, I'm here to break it down step by step with real examples and zero stress. From algebra to functions, graphs to equations, I've got it covered. Hit that like button and let's master math together.
Welcome to right triangles. There's a lot of information about right triangles and the relationships in between the parts of it. And so it's really important that we understand that when we have a right triangle, we have a very powerful amount of information given to us. So first of all, let's go ahead and let's look at a right triangle. So sometimes they draw right triangles in various forms. Okay, I'm going to go over how I would draw it for geometry class as well as how I would draw it differently for a trig class. So we're going to draw this twice. So in a geometry class, they're going to go ahead and they're labeled the vertex, or the vertices, plural, right? A, B, and C. And generally, they go ahead and write the 90-degree angle. Now, A, being right here, opens its mouth, so side A goes right there. And notice that's a lowercase letter. So angle B, or side B, corner B would go with side B, and corner C goes with side C. So that's how I would label it if I were in a geometry class. In a trig class, I'm going to call this alpha, as I know some people think it looks like fish, some people think it looks like the red ribbon sign. It's the first letter of the Greek alphabet, alpha. Here's my 90 degree. So across from alpha is the first letter of the normal alphabet. So this would be the second letter, beta, and B, gamma, which looks kind of like a wishbone, but it's already a 90-degree angle, so we don't have to worry about it, and C. So if you've done anything with triangles, you know that the three corners add up to 180. So here we can write the measure of angle A plus the measure of angle B plus the measure of angle C goes 180 degrees. So if I subtract that 90 over to the other side, then the two acute angles are left to share the remaining 90 degrees. I could do something similar for the other one, but I'm just going to say, hey, instead of angle A, that's where I have alpha, right? Normally I write alpha like that. I'm not sure why I wrote alpha backwards that time. I don't think that's appropriate, but I think it was so I could fit it in. Alpha plus beta is 90 degrees. Okay, so let's draw that correctly. That's kind of bugging me. Apparently I had a moment of writing backwards. So it's kind of important to understand that yes, we can add up, we can get our angles, okay? Whether you're using Greek letters or regular letters, it means the same thing. So like I said, I just happen to like Greek letters for my angles and normal letters for my side lengths so that I don't have to worry about capital and lowercase. I can worry about Greek and traditional. So there's also something out there called the Pythagorean Theorem that's about side lengths. And you'll notice I've labeled the sides the same. And it's the Pythagorean Theorem. And there is a proof you can actually even draw a rectangle and then cut the rectangle into two triangles and make squares with them, and you can find out that the two little triangles made into a square would make the entire rectangle. So made it into a square. So that's kind of a neat thing if you feel like doing that. But that theorem is a squared plus b squared equals c squared. So if you have a right triangle, then you can compute a squared plus b squared equals c squared. The converse of that says if you have a squared plus b squared equals c squared, then you have a right triangle. So it works forward and backwards. I'm not worried in my class about whether you tell me it's the Pythagorean Theorem or it's the converse of the Pythagorean Theorem. I care that you understand that if you have a right triangle, the Pythagorean Theorem is true. If you have a squared plus b squared equals c squared, then you have a right triangle. It goes forward and backwards. Now, Pythagorean triples. If you take the ACT, Pythagorean triples are going to be so nice for you. They are three non-zero numbers that satisfy this. 3 non-zero whole numbers that satisfy a squared plus b squared equaling c squared. So an example of that would be 3, 4, 5. 3 squared plus 4 squared, does it equal 5 squared? Well, 9 plus 16 is 25. Yes, absolutely, check. That one works. Now, because 3, 4, 5 works, any similar triangle is also going to work. So what if I were to take each of these times 6? Okay. So instead of 3, 4, and 5, what if I had 18, 24, and 30? Well, 18 squared plus 24 squared, it is 30 squared. So that's just a proportionality. It's like taking the 3, 4, 5 triangle and blowing it up. It's still going to have those perfect numbers. So any multiple, any scale factor of this 3, 4, 5 is going to work. Another example, 5, 12, 13. 5 squared is 25, 12 squared is 144, and 13 squared is 169, and 25 plus 144 is indeed 169. So that's another example of a Pythagorean triple. I will say this one is going to be the most frequently used one on your ACT. They just may not always have it as a 3, 4, 5. They might do a 6, 8, 10, something to that effect. So if you have a 3, 4, 5 Pythagorean theorem or ratio or leg lengths, then you have a right triangle. So Pythagorean triples, super helpful in the ACT. So how could I find the unknown side length of a couple triangles? So one thing I have students mess up on is knowing what is what. I purposely called this X this time, so you didn't know whether it was A, you didn't know whether it was B, and you didn't know whether it was C. Here's the big thing, is that we really need to think, instead of A squared plus B squared equals C squared, we need to say leg squared plus leg squared equals hypotenuse squared. Okay? A and B and C are just placeholders for what they really are. So how do I know where my legs are? Well, my legs make an L, L for legs. Okay, so here is my L, so those are my legs. And I labeled this wrong. So this should have been the 12, and this should have been the 15. The hypotenuse has to be the biggest side. If the hypotenuse is not the biggest side, you do not have a right triangle. So make sure you're labeling things correctly. Okay? So in this case, we have a leg, we have a leg, and we have a hypotenuse. Now we can fall back to algebra 12 squared because you do exponents first. 144 plus x squared equals 225. And we're going to just subtract that 225 over. Not the 225, the 144. Ooh. So x squared is going to equal 81. Now, when I square root, normally I do plus or minus, but because x is the leg of a triangle, I know it can't be a negative length. So when I square root, I'm just going to use the positive version. The square root of 81 is 9. Now let's think about this. 9, 12, 15. Divide them all by 3. 3, 4, 5. Oh, that's why it worked out perfectly. It was a multiple of that basic Pythagorean triple. It's the only reason why they came out to nice numbers. Okay, let's try another one. Okay, what about this time? Well, L for legs, right? So highlight them legs. Oh, those are the ones that are going to be on the same side of the equal sign. So leg squared plus leg squared equals hypotenuse squared. Okay, there's no variables on the right, so we're just going to do order of operations. Okay, 149. And if you try putting it in the calculator, it's going to give you a decimal. 149 happens to be a prime number, so there is no reducing this radical. We'll just leave it as the square root of 149. And if you wanted to say that it is approximately 12.2, you could. But anytime you do that, make sure you use the wiggly equal sign and say that so that people know that that's not an exact answer, that it is rounded. So depending on what you need your answer for, having a rounded variable might be okay, but make sure that you know when it's okay and when it's not. Okay, so what if I said you have side lengths of 35, 12, and 37? Do you have a right triangle? Well, we got to test, does it work? Now, before we start that, legs are the shorter pieces. So if this is a triangle, or a right triangle, this would be the hypotenuse. So this would be the possible hypotenuse because it is the biggest. So we're going to try that converse. Does this work? Okay. Handy dandy calculator is going to come in. 35 squared plus 12 squared, so I don't make a typo later, is 1369. Okay, well, 7 times 7 ends in a 9. Might just be there. 1369. Yes, it is a right triangle. What about 7, 8, and 9? 3, 4, 5 work. Does 7, 8, and 9? Well, 7 squared plus 8 squared, 9 squared. Are they the same? No, they're not the same. So these would not make a right triangle. It can be a triangle, it's just not a right triangle. Okay, so Pythagorean triples are on there. What else from these right triangles are on the ACT? Sometimes they'll call this next part geometry, sometimes they'll call it trig, as far as how they mark it on the ACT. But I promise you that it's going to be on the ACT somehow, some way. So I would just know these. You have a 30 degree, 60 degree, 90 degree. And you have a 45 degree, 45 degree, 90 degree. And again, I would know these. If you're taking that ACT, I would know these things. Now the 30 degree is going to be opposite of the smallest side. And I'm going to mark the smallest side 1. Over here on the 45 degree, since 2 of them are 45, 2 angles are congruent, so 2 sides are congruent. So they're both going to be marked 1. Okay. Now if you come in here and you do Pythagorean Theorem, 1 squared plus 1 squared equals the hypotenuse squared. So 1 plus 1 is 2, and we get the square root of 2. So 1, 1, square root of 2. 1, 1, square root of 2. And those were our sides, right? Now, could I multiply these all by 5 and get 5, 5, and 5 square roots of 2? Absolutely, yes. That's what the ACT does. They just take the small one and they do scale factors with it. Okay, well, what about the other one? Because I only wrote down the 1. This one was pretty easy. Okay, so you'll notice that 60 is the middle angle, so it opens to the middle side, and then we have the hypotenuse. So turns out they've done a lot of studies, and they've found that anytime you have a 30, 60, 90 triangle, your hypotenuse is double your short side. So now we need to find that missing thing. So we have 1 squared plus something squared equals 2 squared, because we got to find the missing leg, because we don't have the full L. So 1 plus something squared equals 4, something squared equals 3, square root of 3. Now you might be going, but 3 is bigger than 2. I get that 3 is bigger than 2. The square root of 3, though, is not. It's a little bit smaller. It's 1.7. So the square root of 3 is absolutely a leg. Okay? So leg, hypotenuse. Okay? So 1 is the small side, 2 is the big side, root 3 is in the middle. Can we scale them up? Absolutely. In fact, a lot of books will draw them like this. Let me get the 30 in here. $45. Okay. There's our 60. There's our 90s. Okay. So a lot of books will say, I mislabeled that. Ooh. Normally I don't care about which one's which, but for the purpose of this one, I really do want it a little bit better. This is a smaller angle because that's definitely the smaller side. So the books might call this x 2 times x and x times the square root of 3. So they've just taken the 3 things here and multiplied them by x, which means multiplying these 3 by x would give us x, x, and the square root of 2 times x, or x square roots of 2. Either way you want to write it. You can use this to your advantage because it creates ratios everywhere you go. So if you can remember the 1, 2 square root of 3 and the 1, 1 square root of 2, it's going to be awesome, especially when it comes to doing some other stuff that you're going to have in the future with right triangles. So these 2 triangles are really, really important that you just know. And I'm talking about knowing this form without the variables. You can have the x's, but it's more important to know them without it. Okay. So they might give you a triangle. $30, $60, $90, A, B, C, $28. Find A. They might just say that. Well, how disappointing, right? They didn't give us much. But we know we have a 30, 60, 90. So from our memorization, we know that's 1, 2, square root of 3. But from our triangle over here, 30 goes with A. The right angle we don't know. And the other one is 28. Boom, I see my proportion. 1 over A equals root 3 over 28. Okay. Cross product. Root 3 times A equals 28. Divide by root 3. So you could type that in a calculator and you'd get a decimal. It should be less than 28 because A goes with the smallest angle, so A should be the smallest side. So let's check it out. 28 divided by the square root of 3. 16 point something. It definitely is. However, this is not the proper way to write it. So if you remember, to rationalize, you have to multiply by the square root of 3, top and bottom. So it would give us 28 square roots of 3 over, if you type the bottom into the calculator, you'll just get 3. And let's check that, make sure it's the same thing. Absolutely it is, but now we have a integer or a whole number in the bottom, or a rational number. so that we have put it in proper format. If you have a teacher that allows it, could you round it to 16.2? Absolutely, absolutely. Okay, could we have done something similar for C? Yes, we absolutely could have. In fact, the easy way of saying it is, see how you just had to take A, take 1 and double it? So if you took A and you doubled it, which we have A right here, if you were just to double that, you would get C. Or you could go back through the same process and go, we could put C here and we could make fraction. So that proportion is going to hold line true entire time. You just have to make sure that you're lining things up correctly and you haven't memorized correctly. The biggest error is putting the square root of 3 on the hypotenuse. The square root of 3 is smaller than 2. Okay, so trig ratios, perspective is everything. Again, ACT help right here. So I try not to use A, B, and C all the time. But for this purpose I am. I'm going to actually, we'll use D, E, and F. We'll make F the right angle, which means little f. Capital D, so side D. Capital E, so side E. Okay. Focus. Now, no matter what, F is your hypotenuse. You can't change that. It's the longest side. However, when we do some stuff for geometry trig, we're going to stand at an acute angle. So D is an acute angle. So if this is where you stand, D is the opposite leg, and E is the adjacent leg. Okay? So by opposite, I mean we're standing right here. D is all the way across, where we're touching this side E. But what if we move to E? What if we stand at E? Well, now little e is all the way across, and we're touching side D. So see how when our perspective changed, it flip-flopped what was across from us versus what was next to us? So make sure that when we get ready for this next part, you know where your perspective is. Which of the two acute corners are you standing at? I'm not going to have you stand at a 90-degree angle because they are their own host of things. Okay, so here we go. We have three main trig stuff, ratios, okay? They are sine, cosine, and tangent. And when we work with those, we must have an angle. Now, can your angle be a variable? Yes. Okay. Here's the deal though. Right now you only know about degree angles, so if you're using a calculator, my calculator does not say degree in any way, shape, or form on it. So I'm going to have to come up here into my mode. Let me turn down the brightness. And I'm going to have to get rid of radian, and I need degrees. There's a video on what radians are. Watch that later if you don't know already. So I made sure my calculator is in degrees. If you have a scientific calculator, it probably just says deg and rad. You want it to say deg for right now. That way, if you were to type it into a calculator, you're communicating in the same language. Because if I say it's 32 degrees out when I'm in Europe, that means something very different than 32 degrees in the United States. So because sine, cosine, and tangent actually do something, okay, it's kind of like, you know, when you have a square root, you always have to have something inside of it. Same thing goes here. So we're going to abbreviate sine, S-I-N. We're going to abbreviate cosine, C-O-S. We're going to abbreviate tangent, T-A-N. And those buttons are usually on most calculators. You can find them on your cell phone calculator by turning it sideways. But we don't really want to use a calculator with these, so they actually have some meanings and we have some sayings. So, CAH TOA. Okay, this is just a mnemonic device. Anywhere you see an O, it means opposite leg. Anywhere you see an A, it means adjacent leg. And where you see H, it means the hypotenuse. Okay, now the hypotenuse is the hypotenuse. You can't change it. The opposite leg and adjacent leg are going to depend on where you're standing. So you can get it wrong by standing in the wrong corner. So how are you going to remember SOH CAH TOA and what SOH CAH TOA is? Well, supposedly on the internet or whatever, there's a story about an Indian chief, SOH CAH TOA. Okay? So it's just enunciating what we see written here. I know they're nonsense words, but if you say the three nonsense words, then we'll get SOH CAH TOA. All right. If you don't like that and you like a little humor in your life, there's also another saying out there. Might go back to the 70s and things like that, so please forgive me. I'm just saying this saying. You can find it on the interwebs. Some old hippie caught another hippie tripping on acid. So there's a funny haha way of memorizing it. I just care that you can get those 9 letters written down in that order. Here's why. Sine of an angle, and I'm going to use the Greek letter alpha, will equal the relationship between the opposite leg and the hypotenuse. So I just abbreviated. Remember, O was opposite leg, H was hypotenuse. See the O and the H. Cosine of your angle, because you always have to have an angle, equals, oh, it's an A and an H, so it's the adjacent leg and the hypotenuse. And therefore, if you haven't already figured it out, tangent of your angle is going to be OA, TOA, opposite and adjacent. Now, my high school teacher wasn't cute or funny. I just got, oh heck, another hour of algebra. Okay. Again, the little fish looking thing is just a variable. I use it because I do it so often in trig, and I teach trig that I don't want to confuse my geometry students if they see it for the first time. So I just write it out. Okay, so knowing SOH CAH TOA and understanding its meaning is going to be great for the ACT and can actually raise your score 1 or 2 points. So please, please, please understand it. So on the ACT, you might see something like this. Find the sine of 30 degrees. And that might be all they say. So you're going to come over here and you're going to be, okay, well, I know from that video, 30, 60, 90, 1, 2, square root of 3. And I'm standing at this corner. So this is opposite leg, this is adjacent leg, and this is hypotenuse. SOH CAH TOA, sine. So, okay, my answer is going to be sine of 30 degrees. Opposite leg, 1, hypotenuse, 2. Done. My answer is 1/2. Let's check it with the calculator. Sine 30. Absolutely, it's 1/2. Now, had I done sine 60, would it have given me something nice and simple? Nope, that's a big long decimal. Why is the sine of 60 so long when the sine of 30 was short? Well, let's think about this. Sine of 60 degrees. I'm still doing opposite over hypotenuse, but now I'm here. My opposite and my adjacent switched. So opposite of 60 is the square root of 3, and the hypotenuse is still 2. Let's check that out. What is the square root of 3 divided by 2 as a decimal? Oh, 0.866. Makes sense. That's all we're asking you to do here. If you see sine, cosine, tangent, we just want you to make a fraction. That's it. Okay. So we're going to find okay, let's go ahead and let's find the missing part. So we have leg squared plus leg squared equals hypotenuse squared. So x squared plus 9 equals 100. So x squared equals 91, which divides by so x equals the square root of 91. Let's see. 91 I don't think is prime. It's not. It's 7 times 13, but those are prime, so this doesn't have any socks to fold. If you don't know what I mean about folding socks, you might watch my reducing radicals video. So this side is root 91. I want us to find all 3 trig words for k. So find the sine of k, the cosine of k, and the tangent of k. Okay, so we're standing here, so opposite leg. This would be the hypotenuse, leaving this to be the adjacent leg. Okay, now that our triangle is labeled from perspective K, not from any other perspective, it's important to know that we're standing at K. So, CAH TOA. So I need to do sine first. So I'm getting 3 different answers here. So opposite compared to hypotenuse. 3 compared to 10. Boom, done. That's the sine. I don't know how big K is. I don't care how big K is. That's the sine. So now cosine. That would be our adjacent compared to our hypotenuse. Boom, done. And then we have our tangent, which is the opposite over the adjacent. Uh-oh. We have a radical in the denominator. It's all right. We already know it's a reduced radical, so we'll just multiply it by itself. And we get 3 root 91 over 91. So make sure you're always fixing that denominator anytime you have a fraction in it. Now I'm going to do j. Let's do the sine of j, the cosine of j, and the tangent of j. So we're going to do the sine, cosine, and tangent, but we move corners, so those don't apply anymore. Remember? So sine, that's opposite and hypotenuse. So what is opposite from j? The square root of 91. What's the hypotenuse? 10. Cosine, what leg is adjacent to j? 3. And the hypotenuse is 10. And what's opposite for the tangent and adjacent. So let's compare sine and cosine of k versus sine and cosine of j. See how they flip-flopped? That's because our opposite and our adjacent flip-flop. That's why our sine and cosine flip-flopped. So if you're not careful about your perspective, you're going to be standing in the wrong corner and you're not going to get necessarily the answer. So keep that in mind. So these things, especially knowing that 30, 60, 90 and that 45, 45, 90 triangle can really be helpful not only in your school class, but also in an algebra or an ACT. Okay, we're gonna keep going a little bit because we gotta make sure that we can apply this stuff, right? Why would anyone bother using this stuff? So I can see, okay. Okay, let's say you're in a plane and it is climbing at a 5-degree incline. Okay. And it flies 20 miles. Okay, it's climbing at a 5-degree incline for 20 miles. What is your altitude? Okay, let's make a picture of this. We're in a plane. It's climbing. Right? 5 degrees is very small, so I'm sure I drew that too big. Here's the ground. You've gone 20 miles. What is your altitude? Okay, well, the 20 is definitely our hypotenuse. The question mark is where the opposite should be. And if I look at SOH CAH TOA, the only one that includes opposite and hypotenuse is SO. Okay, great. Sine, this time I have an angle instead of a letter, 5 degrees, because it told me 5 degrees. I'm going to put an X instead of a question mark for my opposite, and my hypotenuse is 20. Okay, well, what is the sine of 5 degrees? And we get to round finally. Usually 4 decimal places is correct, so make sure again that you're in degrees. So we have 0.0872. And how do we get rid of dividing by 20? We multiply by 20. So X is approximately 1.7431 miles, because that was in miles. Almost 2 miles, let's see. Let's change that to feet. That way it makes more sense to some people. It's just over 9,000 feet above sea level, or above the ground level, and add whatever that is for sea level, right? So by that, we can actually find out how high the plane is and whether or not is that a good cruising level or whatever. So they're going to calculate things like that so that they can figure it out. So again, make sure your calculator's in degrees. Okay, so what if they say, hey, what is my angle? They gave you a cosine, they want to know the angle. Only when you're missing the angle can you use a trig word to the -1 power, okay? It will find you the missing angle. So you know we have to keep things balanced. So to cancel out cosine, bleh, I need the opposite of cosine. So you'll see that I just took this up here and I put cosine -1 in front. So these are inverse operations and they cancel each other out, just like +5 and -5. So we're left with angle B equals, this is an exact answer. In fact, one year the online book made my trig students type it in that form. And so you have to be careful and make sure that if you're doing online practice, you type it in exactly as they mean it. So we're going to come in here and we're going to use the blue button. So if we know our angle, we use what's in white. If we're looking for our angle, we use what's in my calculator on blue. And it says it's 65.4 degrees. So approximately 65.4 degrees. Do not forget your degree sign. Okay. What if I want to find the angles here? What could I do? Well, if I found angle P, then I could add them up and subtract from 180 and I could get Q. Or if I found Q, I could do the same thing. So I really only need to find one angle and then I can just use adding to 180. But for the purpose of this, we're going to actually do both. What don't we have? We do not have the hypotenuse. So we don't have the hypotenuse. Bye-bye. Okay. So that leaves us with tangent. So the tangent of P will equal the opposite, which is 2, over the adjacent, which is 3. The tangent of Q will equal the opposite, which is 3, over the adjacent, which is 2. So opposite and adjacent flip-flopped. Okay, but I want to find my angle, so I'm going to inverse tangent this. Okay, Q will equal the inverse tangent of 3 over 2. Inverse tangent of 2 over 3. 33.69 degrees. Okay, so could we round that to 34 degrees? Yes. And 180 minus 34 is not 180. Minus another 90, because I forgot, is 56. The other one should be about 56 degrees. Let's check it. $56.31, close enough for you? And actually, if you take this and this, I forgot to put my plus sign in there. There's the two acute angles and our right angle. They do indeed add up to 180 degrees. So that sine, cosine, and tangent, you know, very, very careful. Just make sure you're in your right perspective. If you know this much information, your ACT is going to be great. If you can use this, and you know your 30, 60, 90 has a 1, 2, square root of 3 side lengths, and your 45, 45, 90 has the 1, 1, square root of 2 side lengths. If you know, well, along with if you understand that little bubble, then you're going to be able to really get the geometry/trig part of your ACT going very well.
Thanks for learning with me here on Math with Michelle. If this helped, give it a like and don't forget to subscribe for more clear and simple math lessons. Got a question or topic you want me to cover? And drop it in the comments. Until next time, keep practicing, stay curious, and remember, you've got this.